This is note card 7.3. It says sample means for quantitative variables. The sampling distribution of X bar. So we're looking at the sampling distribution of sample means. So just a quick review what a sampling distribution is. All right. So what I'm going to do is I'm going to take a sample and then plot it, and then take another sample and plot it, take another sample and plot it. Keep doing that over and over and over again for all possible samples in the population. Okay, so we get all these different X bars and we line them up. Okay, so this is a sampling distribution. Each one of these would be a dot on the sampling distribution. And we showed you before that the center of this distribution, that would be called mu of X bar, but we said that the mu of the X bars is going to be exactly equal to the population mean. It's exactly the same thing. Okay. Now this sampling distribution right here, okay, all the X bars are not the same. Okay, one sample might be 50, one sample might be 60, one sample might be 40, whatever. You know, it doesn't really matter what the the units are or what you're studying, but the important part is between each sample there's variability. So this distribution has a certain amount of spread. So this was its center, but it also has a certain amount of spread. Okay. And that right there is this part. The spread of the sampling distribution, or the standard deviation of the X bars, is equal to the population standard deviation divided by the square root of n. So this is as it relates to means. Okay. Quick review, how does this compare to proportions? Okay, if we looked at proportions, we would plot out all these p-hats. Okay, and it has a center. The mean of the p-hats is exactly equal to the population proportion rho. Okay. And it also has, each p-hat is a little bit different. Each p-hat varies a little bit. So the sigma of the p-hats equals rho times 1 minus rho all over n. Okay. So they look different. These formulas look a little bit different depending on whether you have means or whether you have proportions. Right? Now, there are some conditions. We talked about really 3 conditions before. The normal condition, and the independent condition, and the random condition. So the way proportions met the independent condition, we said population is at least 10x greater than sample, which means 10 times greater than the sample size. Okay. How did it meet the normal? We used the large counts condition, which said that n times rho had to be greater than or equal to 10, and n times 1 minus rho had to be greater than or equal to 10. And random just has to come from a random sample. There has to be some element of randomness in choosing or selecting people. All right. Up here, when we deal with with means, those same three conditions have to take place. All right, normal, independent, and random. And random, same idea. Data needs to come from a random sample. All right. Independent condition, same thing. Population at least 10x greater than sample. Okay. But this one we're going to address a different way. Because down here, we don't have a row anymore. So up here, there's no row because they involve means, not proportions. So we're going to talk about that for a little bit. Okay, on your note card, it tells you a little bit about that. It says the 10% condition must be satisfied. The population is at least 10 times larger than the sample. Okay, that's what we refer to as the independence condition. And then this part right here, it just says the behavior of X bars, okay, of the means of repeated samples is much like that of the sample proportion. It says that X bar is an unbiased estimator of mu, just like P hat is an unbiased estimator of rho. Okay. It says the values of X bar are less spread out for larger samples. We saw the same thing with proportions. Okay, which means that, all right, if we take bigger samples, the spread of our sampling distribution is going to be more condensed. The data is going to be closer to each other, just like we see with our pennies. It says their standard deviation decreases at the rate of 1 over the square root of n. For example, you must take a sample 4 times as large to cut the standard deviation of the distribution X bar in half. Remember that last question from the last section where it said the sample size went from 1,000 to 9,000, so it went up 9 times as much, but it only cut the standard error down by 1/3. Okay, it only divided it by 3. All right, it's the same thing here because you have a square root of n in the denominator. So let's read the next 2 parts because this is important. Sampling distribution of a sample mean from a normal population. It says if the population distribution is distribution is approximately normal, then the sampling distribution is automatically also approximately normal. So what does that mean? So if I had access to see the population distribution, right? If this was the population distribution, that was the population distribution of mean, or not of means, just of all the data, All right. Let's say it was given to me in some sort of histogram fashion. Okay. This kind of looks bell-shaped a little bit. Okay. So let's assume that the population distribution, or let's say we're told, is approximately normal. If this is true, then if I were to take a sampling distribution from that population, then remember, a sampling distribution involves all possible samples. Then this, the sampling distribution, is automatically approximately normal. So if you look at if the population is approximately normal, automatically the sampling distribution is approximately normal. Now, what about if we don't know about this? What about if we don't know about the population? So that's the next bullet. Excuse me. It says the sampling distribution of a sample mean from a non-normal or an unknown shape population. If the population distribution is not normal in shape, or we don't know what shape the population distribution makes, as long as the sample size is greater than or equal to 30, then the sampling distribution of x bar will be approximately normal by the central limit theorem. All right, so even if we have a crazy looking population, okay, maybe it's some sort of skewed population. Maybe it's skewed left, maybe it's skewed right, or maybe we just don't know. Okay, these are all populations, distribution. If any of these are true, but if my sample size is greater than or equal to 30, what we would find is that the sampling distribution, even though the population distribution was skewed, the sampling distribution is not skewed. This would be approximately normal. And this would be the sampling distribution. And that right there illustrates the central limit theorem. Okay, so if your sample sizes of repeated samples are at least 30, this is going to be normal, even though these are not. Or we might not even know what the population distribution is. So that's why it's important when we take samples, especially when we're looking at sample means, that we make them bigger than or equal to 30. And then I'm pretty sure that this is going to be approximately normal. That's what the central limit theorem tells us. And that's what the bottom part of this note card says. It says the central limit theorem is important because it lets us turn a non-normal population distribution into a normal sampling distribution. And then that lets us make inferences and probability calculations basically using normal CDF on our calculator, that normal CDF function. Then it says if the sample size is less than 30, then we cannot say with certainty that the sampling distribution is approximately normal unless we were told that the data comes from a normal population. If that's true, it doesn't matter what the sample size is. Okay. So let's look at an exercise. It says the height of all young women, so they're giving me information about a population, follows a normal distribution. So they're telling me that the population is normal, with a mean of 64.5, that's mu, and a standard deviation of 2.5. Those are in terms of inches. So that's mu and that's sigma for the population. Okay. Part A. It says find the probability that a randomly selected woman, one randomly selected young woman is taller than 66.5 inches. Okay. So this one's going to be fairly straightforward. We're told that the population distribution is normal. And this is the population distribution. It's normal with a mean of 64.5, standard deviation of 2.5. All right, so there's where 64.5 is. And I want to figure out what's the probability that she's taller than a single person is taller than 66.5. So I'm trying to find that area of the curve. I'm trying to find the probability that any single woman, okay, so some x value is greater than 66.5. Okay, where x is the height of women. That actually equals height of a woman, young woman, based on the problem. So second, Normalcdf. Okay, so the lower is 66.5. That's where I start my shading. Goes up to infinity. Mean is 64.5, and the standard deviation is 2.5. Enter. 0.212. There is a 21.2% chance that a given young woman is taller than 66.5 inches, which is about 5'6.5", 5 feet 6 inches and a half. All right. Now let's look at part B. It says find the probability that the mean height, okay, so find the probability that we get an x bar, okay, of a simple random sample of 10, okay, so they're telling me the sample size is 10, exceeds 66.5. Show your work, okay. So now, since we have a sample size, and they're asking me to find the probability that the mean height, I mean, this axis becomes x bar. Okay. Now, what did we tell you about the population? We said the population was normal. So that means that the sampling distribution is automatically approximately normal as well. Okay. It doesn't matter that this number is smaller than 30. Okay, so this is going to be approximately normal. All right. So the normal condition, if we write it out, we can say the population distribution is normal, therefore sampling distribution is normal. Okay. Let's check the independence condition. All right, the sample size is 10. So then multiply that number times 10. 10 times 10 is 100. The question is, are there more than 100 young women in the world? Yes. Clearly, there are more than 100 young women in the world. And lastly, we need to make sure the random condition works. How do I know this is random? Because the data tells me it comes from a simple random sample. So I can just say SRS stated. So these are my conditions. I got to check conditions when I do inference. There's no conditions over here because it's not for X bars. They're just for, for one person. All right. So here, that was the mean of the population, 64.5. So over here, we're going to talk about mu of X bar. Okay. But what do you know about the mean of the population and the mean of the sampling distribution? Those values are going to be the same. All right. What changes, though, what's going to change is that area, because this graph is comprised of a whole bunch of X bars. And the spread of these X bars, as sample size goes up, the spread of these go down. So this graph is more compressed than this graph. Okay, this graph is more compressed. All right. So I'm going to do this on another sheet of paper. All right, so I know that mu of X bar is 64.5. But how are we going to find the spread of the sampling distribution? What we're going to have to do is we're going to have to take sigma, the population standard deviation, and divide by the square root of n. Well, so instead of the standard deviation just being 2.5, I have to take that 2.5 and I have to divide by the square root of 10. So we can do this on the calculator, of course. So I have 2.5 over the square root of 10. That's about 0.791. I'm going to store that in my calculator as A. So on my sampling distribution, we already talked about why it's approximately normal. Mu of X bar is 64.5. But now my standard deviation isn't 2.5 anymore. My standard error is 0.791, so it's a much smaller spread. Okay, it's a much smaller spread. So 66.5 is actually would be way out here because it's further out from the center now than it used to be. Okay. So how do I find this? I need to find the probability that an X bar now, it's not just X, it's an X bar, is greater than 66.5. All right. So this sampling distribution is normal, and it follows 64.5 is the mean of it, and the standard error of it is the 0.791, and we can do that in our calculator by using the Normalcdf. So if we put this in, second distributions, Normalcdf, again we're going to go 66.5 to infinity because that's the shaded part I want. Okay, the mean's still 64.5, but the standard deviation is that decimal that I stored as A. So that only gave me 0.0057. So what does this mean in context? There is a 0.57%, okay, that would represent 0.57% chance that a sample of 10 young women would have a mean height above 66.5 inches. One woman likely to be a few inches taller, okay, but the likelihood of 10 young women that their average is that much greater than the mean, it makes sense why it should be considerably less. Okay, because one person can be tall. Okay, but to have 10 women that average out 2 inches above the mean height, not very likely. That's why this is such a small probability. That could happen. It's just not likely to happen. Right? Or if I were sampling the WNBA players, it'd be very likely. Okay? But just in general, no. Not very likely. All right, let's do one more sample. Or not one more sample, excuse me, one more example. I'm a little sick. It says your company has a contract to perform preventative maintenance on thousands of air conditioning units in a large city. It says, based on service records from the past year, the time and hours that a technician requires to complete the work follows strongly a right skewed distribution. So I'm going to stop there and I'm just going to think about this. So the population is right skewed, which means the tail is going to the right. So most jobs don't take that long, but a few jobs take a really long time. So this is like the time to completion, to complete the job. All right. And it tells me that this distribution, the population distribution, has a mean of 1 hour, okay? But it also has a standard deviation of 1 hour. It's a huge standard deviation because of the skewness. It says, in the coming week, your company will service 70 air conditioning units. So that's a sample size. Okay. That says, what percentage of jobs will not be completed within 75 minutes? Okay, within 75 minutes. So what's the probability that my sample mean is greater than 75 minutes? That's what the question's really asking me. What's the probability that when I take the mean of these, it goes over 75? All right. So let's think about the sampling. Let's think about our conditions. Okay. Let's think about what the sampling distribution would look like. Okay. So we have three conditions. Okay. We have random condition. Okay. Now it doesn't say random. Okay. But the 70 that we're going to service, we can think of that as a random sample of the thousands of air conditioning units we service. Okay. So we're going to assume that the 70 AC units we are servicing comprise a random sample. Of the thousands of units we work on. Okay. So that's probably good enough for that one. The independence condition, all right, n equals 70, so therefore n, population n, has to be bigger than 700. Does that work? Yes. Why? Because we work on thousands every year, which is more than 700. So I'm going to say, since we work on thousands of units, population is over 700. Okay. And last condition is the normal condition. All right. Now, the population is skewed. Why is this going to be normal? Okay. Well, here n equals 70, which is greater than 30. So now we can say the sampling distribution is approximately normal by the central limit theorem. And they would accept that too on the AP Stats test. The readers know what the CLT is, especially in this context. All right. So this is going to be normal by the CLT. Okay. So remember, the heights of these are all from different x bars instead of just x's. So what do you know about the mean here? The mean of this, the mean of the x bars, is the same as this. But instead of writing it in hours, 1 hour is the same thing as 60 minutes. So I'm going to think in terms of minutes instead of hours. Okay, what's the spread of the sampling distribution, also called the standard error? Well, we're going to take whatever sigma was, let's think about it in minutes again, divided by the square root of your sample size, which in this case is 70. All right, so if I put that in my calculator, I do 60 divided by the square root of 70, I get 7.171 minutes. And what am I really looking for? I'm looking for this. So this sampling distribution is a normal curve with a mean of 60 and a standard error of 7.171. We can use Normalcdf to figure out what that is. 75, probably about right there. And I want to figure out, it says what percentage of jobs will not be completed within 75 minutes. So if we get it done in 75 minutes, we're good. If it takes longer, we're bad. That's what they're asking for, that area. Okay, again, make this simpler and just store that standard error with whatever letter you want. It doesn't have to be A. It can be, it can be C. So now we're going to run our normal CDF. We're going to go from 75 up to infinity. The mean is 60 minutes. And my standard error, I'm going to put C. Because we're talking about the sampling distribution. Don't put 1 hour here. Don't put 60 minutes, because now we need to find standard error stuff. So there's our probability, 0.0182. That's the answer to the question. This work you still have to show. You have to check the conditions. You have to show that you performed the condition check. Otherwise, they won't give you full credit for that, even if you get the right answer. Right. So in words, there is a 1.82% chance that the mean completion time for the 70 jobs this week will exceed 75 minutes. Okay, so even in this type of company, all right, statistics are important because it helps schedule. All right, that's a small chance. So by doing statistics, okay, this company can schedule work properly and not have to cancel on their customers. Because if they schedule too many people and they don't have enough workers, or it takes too long for their workers to get out of other jobs, that's going to make customers upset. Okay, they're probably going to drop their service. So understanding statistics is important. That's a relatively small probability. So if you schedule jobs 75 minutes apart, there's a good chance you're gonna make it to all those jobs. Now, some jobs obviously are going to be more, some jobs are going to be less time, but the average shouldn't come out to more than 75 minutes. So you take the number of jobs you have in the upcoming week, divided by the number of people, and also divided by the time, and that'll answer the question if you have enough. Right. So that wraps it up for 7.3. Hopefully it made sense and you guys learned a little bit. So stop it.